Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to solve a question related to Fourier series in which we have a function f of x and we have to express this function in the form of series by using Fourier expansion. The question is that we have a function f which depends upon x and the value of f of x is equal to 0 when the limit of x is in between minus pi to 0. It means that f of x is equal to 0 when x is greater than equal to minus pi and x less than 0. And the value of f of x is equal to h when the value of x is between 0 to pi. Limit is that x greater than 0 and less than equal to pi, and we have to find the Fourier series for this function and show that f of x is equal to this expression, and this expression can also be written as in the form of this form. And at the end we have to plot the sketch of this function. We have to plot the graph. And now I am going to solve this question. First, I will guide you how to plot the graph. Actually, we have to plot the graph between f of x and x. Then we have to draw a plane in which x and f of x are contained. Here x, and in this plane f of x. Then after this we have to grade the lines, the value and limits of x and f of x. And actually the value of x varies from minus pi to pi. Then we will break it into small parts. Here 0, here pi, here 2 pi, and in this side minus pi, minus 2 pi, and up to so on, and from this side is also up to so on. And the value of f of x varies from 0 to h, and here at some point we will say that this point is at height h. And now we see that when limit of f of x remain minus pi to 0 and the value of f of x remain 0, minus pi to 0, minus pi to 0, f of x remain 0. And when the limit of x is between 0 to pi, the value of f of x is equal to h. It means that 0 to pi, the value of f of x is h. This is the graph of f of x for these limits. Actually, to complete the graph, we have to expand this graph from this side and also from this side. We see that the graph is like that, minus pi to 0 and 0 to pi, and here also pi to 2 pi and 2 pi to pi. And from this side also we have to expand this graph like this. Actually the original graph is that, and here also we have to expand this graph like this, and from this side we have to expand this graph like this. This is the actual graph of this for the given function. Now we will have to expand the function by using Fourier series. Let's start the solution. Actually we know that the Fourier expansion is for limits minus pi to pi is f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos nx plus bn sin nx. To solve the question, we just have to find the value of a naught, a n, b n, and then put these values in this equation to complete the question. As we know that the values of where a naught is equal to 1 over pi my integral minus pi to pi f of x dx, and the value of an is 1 over pi minus pi to pi f of x cos nx dx, and the value of bn is 1 over pi minus pi to pi f of x sin nx dx. First, I am going to find the value of a naught, as a naught depends upon f of x and the limit of x breaks into two parts. First part is from minus pi to 0 and second part from 0 to pi. That's why we have to break this integral into two parts. First from minus pi to 0 and then from 0 to pi. Let's start. A naught is equal to 1 over pi. First interval is from minus pi to 0, minus pi to 0, minus pi to 0, and in this interval the value of f of x is 0. Then so we will put here 0, and the second interval 1 over pi from 0 to pi, 0 to pi, and in this interval the value of f of x is h dx. Due to 0, the whole function will become 0 from this side, and remaining part 1 over pi, h is constant, so we can take it out of integral 0 to pi dx. The integral of this function is h over pi x 0 to pi. Apply these limit h over pi minus 0. So the value of a naught is h pi over pi. Pi cancel, a naught is equal to h. Then after this I am going to find the value of an, and similarly we have to break this integral into parts from minus pi to 0 and then from 0 to pi. An is equal to 1 over pi minus pi to 0, and in this interval the value of f of x is 0. So we have to put f of x 0 in this interval cos nx dx, and then second interval from minus pi 0 to from 0 to pi, 0 to pi, and in this interval the value of f of x is h cos nx dx. Due to this 0, the whole function in this side will become 0, and the remaining is h. We can take it out of integral because h is constant, 0 to pi cos nx dx. An is equal to h over pi. The integral of cos nx is sin nx over n, and the limit is between 0 to pi. As n is independent of x, so we can write it here h over n pi sin n x 0 to pi. Apply the limits h over n pi sin n pi minus sin 0. Sin n phi always equal to 0 because the value of n is started from 0, plus minus 1, plus minus 2, plus minus 3, plus up to so on. When we'll put here 0, 1, 2, 3, any value. When we put here the value of sine due to pi always remain 0, and sine 0 is also equal to 0. So the function an will become 0. And now we have to find the value of bn. Similarly, here we also break the integral into parts. Bn is equal to 1 over pi 0 minus pi to 0. The value of f of x in this interval is 0, 0 sine nx plus 1 over pi 0 to pi, and the value of f of x in this interval is h sine nx dx. This function will become 0 due to 0, and this side is h over pi 0 to pi sine nx dx. The integration of sine nx is minus cos nx over n 0 to pi. We can write like 0 to pi n pi cos n x 0 to pi. For the limits, minus h over n pi cos n pi minus cos 0. Pn is equal to minus h over n pi cos nx is equal to minus 1 raised to power n, and cos 0 is equal to 1 minus 0. Here we'll put that cos n pi is equal to minus 1 raised to power n. Here we will prove that how we can write this. Cos n pi is equal to minus 1 raised to power n. When n is equal to 0, both sides will give same values. Put n is equal to 0 here. Cos 0 is equal to minus 1 raised to power 0. 1 is equal to 1. When we will put here n is equal to 1, then again this side will give same values. Minus 1 raised to power minus 1. Cos pi is equal to minus 1, and minus 1 raised to power minus 1 is also equal to minus 1. So we can put all the values of n from 0, plus minus 1, plus minus 2, plus minus up to so on. The both sides will give same values. So we can write cos n pi is equal to minus 1 raised to power n. Multiply minus inside h over n pi minus minus plus 1. We can write the bn as bn is equal to 2h over n pi if n is odd, and 0 if n is even. Now I will explain you how we can write the value of bn like this. Actually, when the value of n is odd, this function will give us 2. How? Minus 1 minus into minus 1 raised to power n plus 1. I am talking about this function. When n is odd, minus 1 raised to power n is equal to minus 1. Minus into minus plus 1 is equal to 2. And when the value of n is even, then the value of minus 1 raised to power n is equal to plus 1. Minus into plus 1 is equal to minus 1 is minus 1 plus 1 is equal to 0. That's why when n is odd, this value is 2, and when n is even, this value give answer 0. That's why we write it like here. Now put these values in Fourier series here. F of x is equal to a naught by 2, and the value of a naught is h by 2, plus summation n is equal to, here we will put odd, n is equal to odd, because bn give a finite value, non-zero value when n is odd, and gives 0 value when n is even. So we will use here only odd values. Okay, and an, the value of an is already 0. That's why these whole values will become 0. And then bn here we will use for odd 2h over n pi and sin n x. And now h by 2h over pi, we can take it out of the summation, plus 2h over pi summation n is equal to odd infinity sin nx over n, and which is the required expression. Now the second demand of this question is that this expression can also be written in the form of this. So we have to expand this question, we have to expand this series. F of x is equal to h over 2 plus 2h over pi. Here we will have to expand this summation. First we have to put all the odd values. First odd value is 1 sin x over 1, and second is 3 sin 3x over 3, plus up to so on, all values which includes only odd values. And this is the second requirement of our question.